Hello all and welcome back to this course on computer organization. So having looked at the construction of a register file and having understood how these registers are going to be used at a very underlying level in the microprocessor, we can now shift a little bit to look at the CISC versus RISC argument. What is CISC? CISC, right, is complex instruction set computer, right, and RISC is the opposite in some sense. It is the reduced instruction set computer. Okay. So the name is very intuitive. Basically, the complex instruction set computer is going to give you a wide range of assembly instructions to play with, and therefore you can implement a program in many different ways, some more efficient than the other. Okay, the example of a CISC is basically the x86 instruction set that we saw in the first few weeks, and this is basically there are many architectures which follow the RISC instruction set style. We'll come to that a little later, right? So we are going to look at what is known as the RISC-V processor first. Okay. So how are we going to do this? As usual, we are going to go back to our C program. We are going to compile it and then compare the output of both x86 and RISC-V and understand how these two very different assembly instruction set computers can still handle the very same C program at a execution level. So let's go to our example. So we are going to deal with the following example. We have a main, as you can see here. The main has int x, y and z. X is to 10, y is initialized to 20, and then I am calling the function fn by passing the addresses of x and y. So I am passing by pointer here, right? The function fn, which basically takes int star m, int star n, and I am doing a multiplication of the two values and returning the answer, right? Essentially this is what we are doing, and after I come out of the function in main, I am printing this result z as it is, right? So what we have done till now is to basically come here and set this as x86 MSVC, right? So we have been doing this all this while, and the output that you see out here is very familiar territory for us. We have been looking at this for the first couple of weeks. There is a standard prologue, there is a function execution, and then there is an epilogue, right? Similarly, main is no different from any other function, so that has its own prologue, its body and the epilogue, right? So what we do now, we come here and set this to a RISC-V processor. Okay, we are not worried about GCC or what now. We are just saying RISC-V instruction set. The compiler is not of too much concern to us at this point, right? So what you first of all see here is that the program itself has slightly expanded a little bit. Okay, it's not as small and compact as what it was in the x86. There is a reason for that, which is what we will get into over the next couple of weeks. Okay, so as usual, the way we will do it is we will just focus on the function call. Okay, we'll look at the body of the main and not the prologue epilogue, because in order to understand the prologue and epilogue of main, we need to understand the prologue and epilogue of the function fn, for which we will look at that part first and then we'll come back to the main, right? So we see that this function fn is being called in this particular line here, right? So this is where it is called, and essentially there are the way it is done is quite different from x86. okay, and therefore we need to first go and understand what the register file structure is for this particular processor, right. So let's go and look at this RISC-V instruction set here. Yeah, so we have this, and yeah, okay. So what we have now is something like this. Snipping tool is what I need. Okay, so here is basically the RISC-V register file structure. Okay, so what we see first of all in the RISC-V register file structure is that it has 32 registers. Okay, so if you look at this, the register number starts from X0 and goes all the way to X31, right. So therefore we have 32 registers. Now, how many registers did we have in x86? It was just AX, A, B, C, D. Then we had a stack pointer, we had a base pointer, and then we had, for the string instructions, we had a source index, destination index. It was basically some approximately, so I'll just put this here, RISC-V, and this is x86, okay. So what we basically have is about 10 to 12 registers, okay, 10 to 12 registers. So this itself is a very big difference. First of all, the RISC-V operates with more registers, and there is a reason for that. To understand that, we'll have to look at the clock cycle, the clock period and all that stuff, which we will do in the coming weeks, right. For now there are 32 registers. It's very interesting to note that, for example, register 0 is always a constant value of 0. That means if you want to initialize a register, some other register to 0, then you basically just copy this register x0 into x1, x2 or whatever it is, right. Now, just like the x86, there are certain specialized registers. For example, there was a stack pointer and there was a base pointer. Okay, let us look at that. This is what we had in the x86, okay. That stack pointer is available here, SP. So it is called SP and it is register X2, okay. Now there is one more which is basically called the frame pointer, okay. It turns out that this S0, which is my register X8 in the register file, that means the 5-bit address will correspond to 1000, right. So this is the equivalent of my base pointer, right, as you will see later, okay. Now after this, just like we had seen in the fast call of x86, it turns out that because there are so many registers in the RISC-V, you can even pass a number of arguments, more than just 2, unlike x86, to a function through registers, okay. And therefore you will see that there are function arguments, a bunch of them, about 8 of them are available for passing function arguments, right. And another important register, it's called the return address, RA, the return address, which is register 1. This doesn't exist in the x86 architecture, okay. What is this return address register going to do? It is basically going to store where the program has to return after a call. This is exactly what happened in x86. However, when the call was executed in x86, the return address would be pushed onto stack, and then you would go to the, load the instruction, the instruction pointer, right, the EIP with the new address that you give from the call, right. That is what happened in x86. However, here it seems to be using a register for this purpose. So in summary, what you can conclude from just looking at this is that this is a register centric processor. Okay, it's a register centric processor for a very specific reason. Okay, so with this brief background, let us go ahead and look at what happens to the compilation process and how this program is getting compiled, right? So what we are doing first of all, right, when we look at this, call and all that, it seems to be setting some registers with some values, right, that is going to be consumed by this function. So the function argument passing in this RISC-V is happening through the registers and not through pushing parameters. Now, of course, this comes with a catch, because what happens if I have a function with 100 arguments? Of course, you will run out of registers and therefore eventually you will have to use the memory. So I will leave that as an exercise for you to figure out how that happens in a RISC-V processor, right? But it will be very similar to what happened in the fast call. In the fast call of x86, we said you have only 2 registers which can take 2 arguments. The rest of the arguments have to go through the stack, right? Something similar will happen here also. Anyway, so you call this function fn and you enter the function out here. Okay, you look at the code, it's there here, and this function also has a very similar epilogue, body and a prologue, right? So a prologue, a body and an epilogue, right? So what we need to do is to understand why the prologue and epilogue are designed in that particular way, because remember, the function arguments are mostly coming through registers and stuff like that. So what happens, first of all, what are the kind of instructions that we see in this RISC-V? It is very similar to what we saw in x86. For example, add I, okay, I stands for immediate data. Okay, it means you are adding something and the second argument is going to be an immediate data. Okay, so one more important difference here for us to appreciate, right, is when we looked at the RISC-V, you will have instructions like add I, sp, minus 48. Okay, if you wanted to do the same thing in RISC-V in x86, you would have done add esp, minus 48, right, or you would have done sub. So this is a very important thing, right? We in the x86 you would have a separate instruction to do subtraction and all that, but here you can even get away by doing an add immediate of a negative number, right? So therefore you reduce one instruction. That's why it's called a reduced instruction set computer. However, it doesn't make sense to just reduce these kind of instructions, add, sub, XOR, no. Really, that's not the point of reduced instruction. We'll come to that a little later. So anyway, so here there was one important thing. With this is ESP became ESP, I would say plus 48, minus 48. Right, subtract ESP comma 48 translates to ESP equal to ESP minus 48. So here I am doing the same thing, achieving the same thing, SP minus 48, except that I can technically do SP minus 48 and put it into another register. Okay, so therefore you typically have 3 arguments for any RISC-V instruction, which basically is destination register and then 2 operands that you are going to do this ALU operation with, right? So this is the first difference that we can appreciate by just looking at this generated code. So after that there are 2 other instructions. This is very important. There is SW and LW, right? So what is that? Again, we'll come back here. RISC-V and x86, SW, okay, if you look at the instruction here, it is RA, comma 28, comma SP. Okay, what is this basically doing? It is computing SP plus 28, okay, and putting into that memory location the value of the register RA. Okay, so this is called a store word, right? So this is something we saw very frequently in our x86, all right. So in fact we would have done move ESP plus 28, comma, let's say EAX, right? Then effectively this is exactly what we would have achieved through this ESP plus 28 equal to EAX. So again, it's important to note that this direction was very clear in x86. You always had destination comma source, right? Whereas here that is not as strictly followed, right? However, that doesn't really matter too much, right? So this is what we did. Then you also have a corresponding thing called load word, RA, comma 28 of SP. What is this? It is basically saying RA is equal to compute SP plus 28, treat it as an address, and from that address get this data, 32-bit number, 28 plus SP, right? So this is a load word, okay? And we would have done the same thing in x86 by just swapping these arguments, EAX, comma ESP plus 28. Now, it's important not to get confused by this notation, okay? These are just mnemonics. How you write 28 bracket SP or you say ESP plus 28, all these things don't matter. It's just a way of writing it. Different compilers might do it differently. It's just a notation. Ultimately, all these things get absorbed into the opcode, as we will see in later this week, okay? And therefore, load word and store word is something that will be used quite extensively in the RISC-V instruction set.